Statistics at Johns Hopkins. And today I'm going to talk about Graphons for graph learning. This is also a bootcamp in the same format of the bootcamps before. And before I start, I just wanted to thank Christopher and all the other organizers for the opportunity to speak here. It's particularly special because 3 years ago I was here for this program that Christian Borgs and others, the inventors of Graphons, organized on large networks and graph limits. And a lot of what I'm going to present here are things that I learned then. So just a little bit of logistics. So for the first part, I'm going to talk about graphons and about dense graph sequences, which are sequences of graphs that converge to graphons. And in order to talk about that a bit more formally, I'm going to start by introducing some definitions, for instance, the definition of homomorphism densities, which will then help us define graphons as graph limits. So this is the first interpretation of graphons. And then we're going to talk about the second interpretation, which is as generative models for graphs. And we're going to see that graphs sampled from graphons actually are close to the limit graphon and close to one another in the cut distance. And then finally, in the second part, we're going to move on to the application of graphons in machine learning on large graphs. So we're going to see convolutional GNNs as spectral operators and then look at convergence of spectra in sequences of graphs converging to graphons to talk about convergence and transferability of GNNs on graphs that come from a graphon family. And then, this is going to be the bulk of this bootcamp. And then I'm going to talk a little bit at the end about some recent advances, limitations in sparser graph modeling, covering very, very superficially works by many of you here. And then the idea is to kind of get you interested and then have you talk to people who have been working on these things later. And feel free to stop me at any point with any questions. Okay, so before I start talking about graphons, why graphons, right? So the motivation for looking at graphons and for graph limits more generally in machine learning is that we empirically observe that graph machine learning models scale well to large graphs in the same family, right? So here I give an example where we have two user similarity networks. So you can think of each node in these networks as a user, the edges between them representing user similarities. And then you can think that you have some signal on this network, for instance, the ratings that these users have given to some product, right? So let's say that you, at time t, have a small network of users, but this network is growing. Or you look at a snapshot at a different point in time, and it's much larger, for instance, the Netflix base. You want your models that you train, for instance, for product recommendations on the smaller network to generalize well to this larger network. And indeed, in practice, at least GNN models and convolutional models in general, they do, right? So we see that if we train them on graphs of increasing size here on the x-axis, and then we transfer them to the large graph, to some large limit graph, the error that you make in the predictions decreases, right, with the graph size. So you see this convergence behavior. So we observe this behavior in practice, but what the people that were starting to look at random graph models and graph limits for understanding machine learning on large graphs wanted to do was to understand essentially the theoretical underpinnings of this convergence behavior, right? So the graphon is a very convenient tool to use for this because it is a graph limit, so it works as a proxy for large graphs. And it also works as a graph generative model, allowing us to both identify a family of similar graphs and also to sample representative small graph subsamples on which we can train our models to then transfer to larger graphs, right? And by saving computations, essentially. And at the end of the day, what we're going to see here is that the theoretical underpinning really is that this ability to scale of these models comes from their continuity with respect to these sequences of growing graphs that converge to graphons, right? Or insert any graph limit here. There are different convergence paradigms, but here we're going to talk about graphons specifically. Okay, so before I introduce the definition of a graphon, we need to kind of set up a few important definitions. So the first one is the definition of a graph homomorphism, which most of you here are familiar with. So a homomorphism is this map between two graphs, a graph F and a graph G. And we say that a homomorphism from F to G is essentially an adjacency preserving map, right? So gamma is a homomorphism if it maps nodes such that an edge on the graph F is also an edge on the graph G, right? And here I have, I don't know if you'll be able to see, but I have an example of a small triangle F, and then you can see that there are many ways in which you can map this small motif F into the graph G. You have essentially two triangles, right? So you can look at all the permutations of the labels of F and place this triangle on top of the two triangles of G, and this gives you different homomorphisms. So in addition to defining the homomorphism, we also need to define this quantity homFG, which is just the number of the total number of homomorphisms from a graph F to a graph G. In this example, we have 12. And then the quantity that is useful for graphons is actually the homomorphism density, which is essentially the ratio between the number of maps that are homomorphisms in your graph, between your graphs, right, and the total number of ways that you could map the nodes in F to the nodes in G without needing to preserve adjacency. And so in this example, this is 3/16. Okay? And why do we care about graph homomorphisms? Well, we care about them because they are used to define what it means for a graph to converge to a graphon. So essentially, the way this definition works is we're going to look at graph motifs, which are any unweighted and directed graphs that are free of self-loops. And we are going to look at the sequence of density of homomorphisms from F to graphs GN in a sequence. And if these homomorphisms converge, these densities of homomorphisms converge, then this means that this graph sequence has a limit, and that the limit is graphon, right? And what has to happen here is that these densities of homomorphisms have to converge for every possible motif F, okay? And what is a graphon? A graphon is a bounded symmetric measurable function W. It maps points from the Cartesian product of some node sample space with itself to 0, 1. Typically, we'll consider the node sample space to just be the unit interval, either natively or via measure preserving transformation, right? You can think of having like more general node sample spaces omega, but you can map them to 0, 1. And the easiest way to interpret a graphon, which is already not a difficult object to interpret in the first place, but in the context of graphs, the easiest way to interpret this graphon is as a graph with an uncountable number of nodes, right? So you can think of the points in your node sample space as the nodes, and the graphon values evaluated at pairs of nodes as edges or edge weights. Okay, so I told you about how we use densities of homomorphisms from any motif to GN to define convergent graph sequences. I told you that the limit of these convergent graph sequences is a graphon. But what is the density of homomorphisms actually converging to, right? So the limit of the homomorphism densities is the graphon homomorphism density for all motifs F, right? And it is given by this expression. Now you're integrating over the edges in the graph F. And perhaps a more interesting way to interpret the density of homomorphisms on the graphon is as the probability of sampling that motif F from the graphon W. Okay, so here we already start to see that besides having this interpretation as a graph limit, the graphon can also be thought of as an object that we can sample graphs, in this case motifs, from. Okay, and the homomorphism density gives us the probability of seeing these motifs. So here I just have two small examples of how you can think of graphons as limits of graph sequences. In this case, I have a sequence of Erdos-Renyi graphs converging to an Erdos-Renyi graphon, right? This is just a graph with constant edge probabilities. And in the second slide, in the second example, I have a sequence of stochastic block model graphs, then stochastic block model graphs converging to stochastic block model graphon. And the idea here, like you have to believe me that these graphs converge in the sense that densities of all motifs converge. But what is interesting is you can also see that there is this overall, like visually, right? Like the global structures of these graphs are converging in some sense to the global structures of the graphons. You can see that here you're almost constant. Here you can see the two communities, and so on. Okay, so this is the interpretation of graphons as graph limits. But like I said earlier, besides being interpreted as graph limits, graphons can also be seen as graph generative models. And there are different types of graphs that you could sample from a graphon. Here I give two examples. So the simplest type of graph that you could sample would be deterministic weighted graphs. So in order to sample these graphs, you first have to sample the nodes. You could sample them, for instance, on a grid over the unit interval. You could sample them uniformly at random. That gives you your nodes. And then once you have your nodes and they're fixed, they're identified with these labels UI, you define weighted edges with edge weight WU, Y, UJ, right? That will give you a complete graph. And even though it might have random nodes, it has deterministic edges. So this is not that interesting because it's complete, and we're interested in more interesting graph sparsity patterns, I guess. The more interesting type of graph that you can generate from a graphon are stochastic and weighted graphs. So now you're going to sample your nodes in the same way, but you're going to instead of having a complete graph with edge weights given by the graphon, you're going to sample edges with probability given by the value of the graphon at these node pairs. So by Bernoulli with probability W, Y, U, J. And here is an example of how you might see the graphon as a graph generative model, right? This is literally the same figures as before, just like shuffled a little bit. But in fact, we have generated all of these graphs by sampling, as I described before, right? Like by sampling nodes uniformly at random from 0, 1, and then sampling edges Bernoulli with probability given by the graphon. Okay, so a natural question that you might have is like, okay, I know what to look for to be able to tell if a graph sequence is convergent, it's converging to a graphon. And I know that I can generate graphs from a graphon, but do these graphs that I generate from the graphon converge to the graphon in the homomorphism density sense? And this corollary in a very nice book by Lovash actually says that they do. So these stochastic graphs that you sample from the graphon converge as their size tends to infinity, right? So the convergence is in probability, of course, because these are stochastic graphs. And this is a simple but nice result because it's telling us that if we sample two graphs, GN and GM, with different number of nodes from the graphon, these graphs must be close, right? Because they form a convergent sequence. We'll formalize what it means for two graphs to be close, under which metric they're close in a little bit. But this is what this result is essentially saying. Okay. Now, when we get to the problem of actually measuring distances between graphs, right, to be able to say if they're close or not, we have defined densities of homomorphisms as things that we can inspect to be able to tell if graphs converge. And we could, for instance, try to measure graph distances by computing these homomorphism densities for a motif F and comparing them, right, for two graphs. However, the notion of convergence says that we need the densities of homomorphisms to converge for all motifs F, and there's infinitely many motifs. So this is impractical. It's impractical measuring graph distances in this way. And something that is slightly more subtle, and that we'll discuss a little bit more later, is that homomorphism densities are essentially these like you're looking at densities of local motifs, right? So it's a very local notion of similarity. And a special thing about graphons is that they're similar in both a local and a global sense. So maybe a metric that takes, yeah.
Now, just a quick question. So also the other challenge, wouldn't this motif, like as it goes to infinity, be uncountable? Like, because they are, you know,
like the motifs themselves are uncountable, right? Yeah. I guess, yeah, that's a good point. I don't know if you could restrict yourself to motifs of size up to n, but even then you can't. Okay. Yeah, so then in that case, I mean, it's not, right. That's another reason why it's impractical. Yeah. Okay. All right, so what are notions of distances that we have for graphs? So starting simple, we can start from graphs with the same size and with the same labeling, right? So that we don't have to care about node permutations. So there are two distances that you can consider. One is the L1 norm, or the edit distance. And this distance, I say that it's local because if you just remove one edge, it doesn't matter what that edge, what the role of that edge is on the graph. This distance is going to change by the same amount, right, if you remove one edge. On the other hand, you have the cut distance, which is a more global type of distance because it is more sensitive to where the edge is coming from, right? So if it's coming from a cut or not, right? And this cut distance is defined in terms of the cut norm, which is essentially given some matrix B, finding the size of the largest cut. But the cut distance itself, in this case where we have fixed labelings and same sizes, is obtained by essentially computing the cut norm of the difference between the adjacency matrices of both graphs. Okay? So now we, going from graphs of same size and same labeling, the next level up is to look at graphs of same size but different labelings. And in this case, we define the cut distance in a very similar way to which we defined the cut distance before, but now looking at all possible permutations of the labels in one of these graphs and fixing the labeling of the other. And then the cut distance is the minimum over all of these, of the cut norm of this difference over all permutations. So this cut distance is, as it is defined for graphs with different labelings, is invariant to node relabelings. Now, to extend this to graphs of different sizes, which we're going to need to talk about convergence, convergent of graph sequences that are growing, we need to define induced graphons, which are graphon representations of a graph. So the way you define an induced graphon, for instance, for this graph here, right, like you have the adjacency matrix of this graph. Very simplistically, you can think of just plotting this, like fixing a labeling and plotting this adjacency matrix on the unit square, right? And then this is equivalent to essentially defining like a step function on the unit square with steps given by the entries of the adjacency matrix. And again, always fixing a labeling before you do that. So we call this the graphon induced by the graph G, okay? And we can do this for graphs of any size. The only thing that changes is the length of these intervals corresponding to different nodes. Okay, so now to compare graphs of different sizes using the cut distance, what we'll do is we'll compute the induced graphon for both of these graphs and measure the distance between them by using the extension of the cut norm for kernels, right? So this is, again, just looking at the size of the max cut in this kernel. We define the cut distance between two graphons by essentially finding the cut norm between the cut norm of the difference between these two graphons. And again, we have to look over all measure preserving bijections, right? Like the generalization of permutations, and we take the infimum over all such measure preserving bijections. Okay, and that gives us the definition of cut distance not only for graphons but also for graphs via their induced graphon representation. So why are we doing all of this? Remember that we talked about how we can use graphons to sample graphs. These graphs converge in the homomorphism density sense to the graphon. And we asked ourselves, okay, they converge, but what it means for these graphs to be close to one another, right? So the second sampling lemma, which is also a result by Louvache and by his collaborators, says that if we generate a graph by sampling it from a graphon, then with high probability, it is close to the graphon in cut distance. Okay, so this is decreasing asymptotically with n. And this is interesting because not only is it answering the question of whether graphs sampled from a graphon are close to one another and formalizing the sense in which this is the case, but it also shows this, obviously in only one way at this point, but it shows this equivalence between convergence in the homomorphism density sense and in cut metric. And in fact, these two are equivalent for graphons. Yes, so any graph sequence that converges in the homomorphism density sense also converges in the cut metric and vice versa. And just to conclude this part, going back to what I was alluding to earlier when I was talking about local and global notions of convergence, there's these very nice interpretations that we can make of convergent graph sequences by either looking at the homomorphism density notion of convergence or the cut metric notion of convergence, right? So convergence of homomorphism densities is telling us that densities of motifs in graphs sampled from a graphon converge, right? So we have this convergence in a local sense, right? Because these motifs can be as small as possible. Cut metric convergence is looking at size of max cuts, right? So it's a more global notion of convergence. But for graphons, these two are equivalent. So you have this, graphons are really special because you have both local and global convergence. And this is thinking about the graphon as a limit object, but when you think about it as a generative model, you also get this interesting interpretation from both notions of convergence, both because we can think of the homomorphism density as the probability of sampling a motif from a graphon, and through the sampling lemma, we actually see that these graphs that we generate by sampling from the graphon are close in this global distance metric, right, in the cut metric. Okay? Any questions about this before we move on? Okay. I think I'm going a little too fast, so I'll try to slow down.
Question.
Yeah.
Can we estimate like distance measures and things like that using a graphon instead of actually computing it in the real graph?
So are you saying, like, for instance, estimate distances between two graphs by using the graphon?
No, if there's a huge graph and I have like a shortest distance computation time, can I estimate it using a graphon-induced graph? Yeah,
that's a good question. That's essentially at the core of what we're going to do here. So we're going to try to estimate, or either we know like the graph limit model, or try to do computations, calculate statistics in the graph limit model, right? Or on a sample, on a representative sample, and then transfer to any other sample. That's the idea. Mm-hmm. All right, so now let's talk about the use of graphons in graph machine learning. And I'm primarily going to talk about how graphons have been used to understand convergence, scalability, transferability of GNNs. So we're going to focus on this primarily. And there's a good reason for this, right? Like, one, this is a workshop on, not on GNNs, but we've been talking about GNNs all day. And not only that, but more importantly, GNNs have achieved great empirical performance in practice. There's a whole community working on this. And not only does it have good empirical performance, this performance is supported by many, many theoretical properties, some of which we saw today: invariances, expressivity, stability, and a lot of you here today have worked in characterizing and formalizing a lot of these properties. So that's why we're going to focus on them. And specifically, I'm going to focus on convolutional GNNs. And I'm going to represent their layers, or write their layers as, in this form, where XL here is going to be my node features, or what I'll often call a graph signal on the nodes of my graph. S is going to be some matrix, some graph matrix, taking the sparsity pattern of the graph into account. In this case, it will always be the adjacency. And my learnable parameters are HLK. And I'm looking at these convolutions with what I'll call K-filter taps, because these are, you could think of this as like actually one whole linear GNN. But I like to express the convolution in this more general form, because then we get all the nice properties of convolutions, right? You could, if you let K tend to infinity, you can represent any analytic function with just one convolutional layer. And moreover, you can particularize this definition to many of the most commonly used GNNs in practice, such as most linear MPNNs, GCN, GraphSage, and others, okay? And we'll focus, like I said, on the adjacency matrix, but results for GNNs where this matrix S here is the Laplacian would follow by considering the limit graphon Laplacian, which you can define from your graphon. Okay, so what I'm going to try to do here, just to give you an introduction, is I'm going to try to define these equivalent limit objects to GNNs on graphons. And in order to understand why GNNs scale, I'm going to try to explain that through convergence of GNNs to the corresponding graphon limit objects, right? So in order to do that, I need to essentially generalize all of these things that I defined here for GNNs. The first one of which are the node features or the graph signal. So a graphon signal is simple to extend from graph signals to graphons. It is just a function. Now it's a function mapping points from your node sample space, in this case 0, 1, to the reals. And here specifically, I'm going to focus on finite energy signals, or equivalently signals in L2. And it is very easy to see from this definition that a graphon signal is also a generative model for a graph signal, right? So if I sample a graphon by sampling points from my node sample space, I can sample my signal at those same points to define the value of my node features on that graph, on that sample graph. Okay. To define graphon signals as limits, we have to be a bit more careful. Because first of all, we're trying to compare discrete and continuous objects, and second of all, we also have the issue of permutations, right? We need to retain the exchangeability of the graphon model. So the way in which we define convergent graph signal sequences is by first defining the graphon signal induced by a graph signal, right? So that is just a step function with steps given by the value of your graph signal. And then we'll say that a sequence of graph signals converges to a graphon signal, where we have the graph sequence and the graphon specified, if both the graphs converge to the graphon in the homomorphism density sense, and if there exists a sequence of permutations on the labels of your nodes, such that your graph signals converge to the graphon signal in the 2 norm. Right? Because we're considering finite energy signals here. Okay, and I just left this note here to say that because we were talking about the cut distance earlier, right? This is not really the cut distance, but if you fix this permutation sequence such that this happens, this same sequence of node permutations should ensure convergence in the cut norm. Okay, so the next thing that we have to generalize is this notion of message passing, right? Or diffusion, shift, whatever you call it. And for graphons, that is the graphon or graphon shift operator, which is the integral linear operator defined or with kernel given by the graphon W. So this is just simplistically, right, like just a matrix multiplication in infinite dimensions. And we call it graphon shift operator because it diffuses messages over or signals over the graphon. And an important property of this operator is that, because W is bounded, it's a Hilbert-Schmidt operator. It has finite Hilbert-Schmidt norm. And because of that, and because it is self-adjoint, right? Because W is symmetric, it has a discrete real spectrum given by eigenvalues lambda I and eigenfunctions phi I. Okay, and this will come in useful soon. Okay, so we have generalized graph signals. We have generalized the adjacency operator. Now we're in a good place to generalize the graph convolution. So graphon convolutions will have the same algebraic structure as our graph convolution, right? It's just a shift and sum operation. But now the shift will be given by the graphon shift as opposed to the adjacency matrix or the graph shift. And so we'll define graphon convolutions as this map from L2 to L2, to L2 functions to L2 functions. That is mapping these graphon signals, these input graphon signals to these output graphon signals via these polynomial expressions here, where each one of the TWK is now graphon, like a sequence of graphon shifts, right, is defined recursively in this way. Okay? All right, so now that we have a definition of graphon convolution, we can also define a graphon neural network, right, or a convolutional graphon neural network, which again has the same algebraic structure as GNN, and so where each layer is going to be given by the composition of a pointwise nonlinearity with a graphon convolution with learnable weights HLK as before. And the nonlinear activation function here, sigma, is easy to generalize, right? We have generalized graph convolutions to graphon convolutions. Because the activation function is pointwise, it's simple to generalize. It goes from node-wise to pointwise on the node sample space. And so we have our graphon neural network. But what is interesting about the graphon neural network is that if we fix the set of learnable coefficients HLK here at all layers and for all taps, then the graphon neural network can be seen as a generative model for GNNs, right? So you can think of, you have your graphon signal, and then you define I'm calling it graphon NN and WNN. And if you fix the set of learnable weights H, then you can instantiate GNNs by essentially sampling graphs from the graphon and sampling the corresponding graph signals from the graphon signal. Okay? So a natural question is now, okay, do these GNNs that I sample in this way converge to the graphon NNs? Or more generally, if I have a sequence of graphs converging to a graphon and a sequence of graph signals converging to a graph signal, if I fix my parameters H, does the GNN converge to the WNN? So intuitively, we think the answer should be yes, right? And it is yes. But we have to prove this, right? And one possible avenue to proving this convergence is, given that the GNN is parametrized by the adjacency and the graphon NN is parametrized by the graphon operator, we can try to prove convergence of the adjacency or the induced graphons to, or the operators induced by the induced graphons to the limit graphon operator. And this is not too difficult to do because we know that the graphons converge, the induced graphons converge in cut norm up to permutations. And we have all of these very nice relationships, inequalities relating the cut norm to operator norms and LP norms. And so we could show operator convergence by leveraging convergence in cut norm. However, there's an issue with this approach, and the issue with this approach is that any results that you get by using this approach will depend on the convolution depth k and on the neural network depth L, right? And this is unsatisfactory for two reasons. One, if we bound k and L, that restricts the functions that we can approximate in our linear layer using the Taylor series, right? At the end of the day, when you look at convolutions in the spectral domain, you can be doing Taylor series approximations of analytic functions. And moreover, once you go beyond asymptotic convergence and you look at non-asymptotic rates, your rates are going to depend on k and L, which can give you overly loose bounds, especially if you have large depth, because you're ignoring the magnitude of the weights hk in the layers of your GNN, right? You might have like a very deep GNN, but where all the weights hk have low value, and so you might be your bound might be too conservative, not too conservative, might be too loose here. So to try to circumvent these two issues, what we do is we carry out this analysis in the spectral domain, which is the spectral domain of the adjacency matrices of these graphs, right? So in the case of graphons, we're dealing with undirected graphs, so the adjacency matrix always admits an eigendecomposition. And the spectral domain representation of the convolutions can be obtained by essentially relating the graph Fourier transforms of the inputs and outputs of this convolution, and these graph Fourier transforms are nothing more than the projection of your signal x onto the eigenvectors of your graph. Okay? So if we take these graph Fourier transforms and we relate them using the expression of the graph convolution and the eigendecomposition of S, we see that in the spectral domain, the graph Fourier transforms are related by a polynomial which has the same coefficients as our graph convolution polynomial in the node domain, but is now a polynomial on the eigenvalues of the graph. Okay? And this is interesting for three reasons. One, it shows us that the convolution is discrete in the spectral domain, meaning that each spectral component of the output only depends on the same spectral component of the input and on the function h of lambda evaluated at the ith eigenvalue. Two, because it's pointwise, right? So these are more or less the same thing. And three, because it only depends on the weights hk of the convolution and the eigenvalues lambda, right? So it's fully determined by these two things in the spectral domain. So this is just a pictorial illustration of what I was talking about. So in the spectral domain, you can represent a graph convolution as a function in 1D, which is great, right? Because we don't have to do with the graph here. It is just some polynomial given here by this red function. And if you want to evaluate this specific filter or convolution in a given graph, you just have to instantiate this function at the eigenvalues of that graph. Okay, so in the same way that we could obtain the spectral representation of the graph convolution, we can do the same for graphon convolutions. For graphon convolutions, because the Hilbert-Schmidt operator is self-adjoint, and because we have eigenvalues and real eigenvalues and eigenfunctions that are uncountable, we can define the analogous of the graph Fourier transform, the graphon Fourier transform, by simply projecting these input and output signals onto the eigenbases of the graphon. And then if we do that, we see that the input and the output of the graphon convolution in the spectral domain are related by also a polynomial that is, again, pointwise and discrete, and only depends on the weights of the convolution and the eigenvalues of your graphon. Okay? And what is interesting here is that if the weights hk are the same, the spectral responses of the graph and graphon convolutions are going to match. So essentially you have this picture here, right, where again you have the same spectral, the same function h of lambda if the weights hk are the same, right, so the same polynomial. The only thing that changes is whether you evaluate this at the graph eigenvalues in green or the graphon eigenvalues in blue. Okay? So this should give you an idea of where we're going, because we're trying to prove convergence of graph convolutions to graphon convolutions. And I told you that their spectral representations are the same in the spectral domain. The only thing that we're missing is essentially convergence of graph eigenvalues to graphon eigenvalues, right? If graph eigenvalues converge, then the graph convolution converges in the spectral domain, given a convergent graph sequence. And graph eigenvalues indeed converge to graphon eigenvalues. This is also a result proved by Borgs, Chase, and others. The result simply states that if, here I'm just like assuming an eigenvalue ordering, I order my eigenvalues according to their sign and in decreasing order of absolute value, and I can show that the normalized graph eigenvalues, normalized by n, the graph size, converge to the corresponding graphon eigenvalues of same index. And here, just for curiosity, I just include a proof sketch. You can find the full proof in Lovage's book. But the idea is to combine the fact that densities of homomorphisms of case cycles can be expressed in terms of eigenvalue polynomials with the convergence of homomorphism densities. And then if you do this for a bunch of case cycles for k greater than 4, you're able to show convergence of the eigenvalues 1 to 1. Okay? But the takeaway here is, if my weights hk are the same, graph convolutions converge in the spectral domain on a convergent graph sequence because the eigenvalues of the graph converge to the eigenvalues of the graph. So this is our first convergence result.
We have sort of implications as to how to design an MPNN, because it seems like you have to scale so some MPNNs divide by the size of something and some don't, so it seems like you have to divide by the size of the graph.
Yeah, great point, right? So I didn't show this when I was kind of talking about the definition of GNN that I was going to use, but your adjacency has to be scaled by n, right? Your shift operator has to be scaled by n in order to have this convergence. Any other questions? Yeah.
So if you have the convergence of some of these lambda to the k, but not for all, then that means that for those that you have the k, you have the convergence of the k cycles. Is there like an if and only if you don't have all of them?
I don't think you can prove convergence of the eigenvalues if you don't have convergence of these homomorphism densities for all the CK. And in fact, you need convergence of all of them, right? Because the graphs are converging in this homomorphism density sense, and the CKs are motifs. So that's needed. Okay. Any other questions? Okay. All right. So this is good. Like, we get our first convergence results in the spectral domain. But it's limited because GNNs operate on the node domain, right? So I'm saying there's this equivalent representation of my GNNs in the spectral domain, but these GNNs are operating on the node domain, and I haven't shown convergence in the node domain. If we want to show convergence in the node domain, we have to project back into that domain, and we do that by taking the inverse Fourier transform, essentially, of our signals y. And in fact, we know that the spectral representation relates the Fourier transforms, which I'm representing here with this hat notation. And then we have to take the inverse Fourier transform of this whole thing, which is just projecting back onto the eigenvectors Vj. So we need convergence of both the graph and the inverse graph Fourier transform in order to have convergence in the node domain, or in order to extend this convergence results to the node domain. And needing convergence of the graph Fourier transform and of the inverse graph Fourier transform means that, in fact, we need convergence of the graph eigenvectors, right? Because the Fourier transform is nothing more than projecting our signals onto these graph eigenvectors. And the good news is we can get this convergence from the Davis-Caron theorem with a few caveats, right? So what this theorem says is that if I look at the spectral projectors onto the jth graph eigenfunction and the jth graphon eigenfunction, the distance between them in operator norm is upper bounded by something that depends in the numerator on the operator norm distance between my graphon and my graph, and in the denominator on this, what I call this eigenvalue margin, which is something very close to the spectral gap, like spectral radius, sorry. Like it's essentially like the smallest distance between any other eigenvalue in the spectrum and the jth eigenvalue for which you're looking for the distance between these spectral projectors. And why is this problematic? Because what the spectral theorem for Hilbert-Schmidt operators tells us is that even though the graph eigenvalues converge to the graphon eigenvalues, because this operator is compact, it has bounded Hilbert-Schmidt norm, this spectrum is contained between -1 and 1. But it's uncountable, right? So it has to converge somewhere, and it converges at 0, which is the only point of accumulation, right? So what this implies is that, sure, like you have eigenvalue convergence, but this convergence is not uniform. You need larger and larger graphs to get like epsilon convergence close to 0. And so if you're looking at eigenvectors associated with small eigenvalues here, this denominator here becomes a problem, right? So it's hard to show convergence for all eigenfunctions from this. Now there's two alternatives here to address this problem. The first one is to look at what I'm calling C-band limited signals, which are signals that only have spectral components associated with eigenvalues larger than C in magnitude. So that's one thing that you can do. And similarly, what you could also do is you could not restrict yourself to band-limited signals, but restrict yourself to low-pass filters. It might be a little counterintuitive because these are like larger eigenvalues. I'm calling them low-pass filters, but like if you look at eigenvalues of the adjacency, those correspond to like low frequencies. Eigenvalues of high eigenvalues of the adjacency correspond to low frequencies, while low eigenvalues of the Laplacian correspond to the low frequencies. So this is a little confusing, but forget about this. What you can do is you can essentially define these filters that have a cutoff at C, right? So that essentially attenuate or eliminate all spectral components between -C and C. And then this would ensure that we only need to look at eigenvalue and eigenvector indices J for eigenvalues greater than C, which essentially fixes the denominator here, and then allows us to use the Davis-Caron theorem to prove convergence of eigenvectors. Okay? So from here, we get our convergence of eigenvectors, we get our convergence of graph Fourier transform, inverse graph Fourier transform, which means we get convergence of convolutions in the node domain for C-band limited signals and for low-pass filters, which is fine, but it's still unsatisfactory because, one, these band-limited signals and filters are not descriptive enough, right? Like they don't span like the space of all possible signals and filters that you can have. And moreover, these filters with discontinuities, they can't really be represented as graph convolutions, right? As those polynomials in your adjacency matrix. So we want to be able to do a little bit better than that. So what you can do is, instead of considering filters that are attenuating these spectral components, or even filters that are constant for these spectral components, right, which would be essentially amplifying them all in the same way, is you can consider filters that vary very slowly in this minus C and C interval. And what this means is that any error that you make here due to these spectral components is going to be, or not the error per se, but like the spectral components are going to be amplified very similarly, which means that they won't contribute much to the error. Okay, and as long as this area is not too large and doesn't comprise much of the spectrum, this shaded area is small, right? So it's small for small Lipschitz constant. So if the filter is almost constant here, we are good. And so I'm not going to go into the details of the proof. It's not that interesting anyway. I have the proof idea that I'll discuss in a little bit. But if you consider filters that are Lipschitz in this sense, right, so that are Lipschitz in the spectral domain, then, and you have a sequence of graph signals converging to a limit graphon signal, as long as the spectral response is the same for both the graph and the graphon, and it is Lipschitz, then we can show asymptotic convergence of the graph convolution outputs to the graphon convolution outputs in the node domain. So we get our convergence result for this class of filters, right? And the proof idea is the following. So we're going to split, you're going to analyze essentially convergence of each spectral component of your output signal. And then you're going to split that analysis into the spectral components associated with eigenvalues greater than C in magnitude and lower than C in magnitude. The convergence of those spectral components associated with eigenvalues larger than C follows from low-pass filter convergence. And for lambda less than C, you're going to use an epsilon delta argument, letting C vanish with epsilon. And so you get convergence of the convolution from this. And GNN convergence follows immediately by just noting that the nonlinearities that are used in practice are all one Lipschitz, right? So Ruiz, sigmoides, and so on. And so essentially all these layers are stable to this growth, right, in this dense graph convergence sense. Okay, so so far we talked about convergence of graph convolutions and GNNs in the spectral domain. That wasn't enough. We're able to translate it into the node domain with as few assumptions as possible. And that is nice because it helps us understand why GNN scale in practice, right? There's asymptotic convergence results. And so it helps understand why we in practice observe this transferability curves, right? When we train our GNNs on smaller graphs and transfer to larger graphs. But for this result to be useful in practice, we also need like a finite sample or non-asymptotic version of the bound. Because for like a practitioner, the things that you're interested in are, you know, if I train on a smaller graph, transfer to the larger graph, what is the error that I make at the output, right? What's the actual error that I make as a function of n? What does it depend on, right? Like what are my design decisions that I have to make to make it as small as possible? And or the other way around, right? Like say that you have like error allowance. How do you decide how large your training graph has to be in order to meet that error allowance? So this non-asymptotic or finite sample result is sometimes called, well, often called transferability of graph convolutions. Here I have a statement of this result for graph sampled from a graphon. I'll discuss related results for other graph limits later. But this is essentially just the finite sample statement, the non-asymptotic statement of the convergence results. But it's interesting because here we see essentially what that convergence depends on, right? So two quantities that it depends on have to do with the graphon and with its spectra. So the first one is the number, like you fix some bandwidth C. That this quantity NC is what we call the C-band cardinality of the graphon, which is the number of eigenvalues that are greater than C, which is always finite. And the C eigenvalue margin, which is as before. And what we see is that the rate of convergence here depends primarily on the Lipschitz constant of your convolutions at all layers of the GNN. Here, actually, I'm only talking about graph convolution. So the Lipschitz constant of the convolution, and on this, both the C band cardinality and the C eigenvalue margin. This term here is not very important. It essentially depends on how close the graph signal is from the graphon signal, but it has to do with its sampling error from sampling the graph signal. And then it also depends on this leftover term here that doesn't vanish with n. But before I discuss these terms in more detail, I just want to make a note on rates. So you notice that I left these results in terms of the operator norm difference of the graphon and the induced graphon, right? So the graphon induced by the graph. And in terms of the norm difference between the graph signal and the graphon signal. And this is because there have been, people have come up with different rates, right? So if you make Lipschitz assumptions on both your graphon and your graphon signal, you get 1 over n rates. If you don't make any continuity assumptions at all and use essentially the rates coming from the sampling lemma for cut norm, then you get these 1 over the 4th root of log n, right? So it makes sense that it would be slower because you're not making any continuity assumptions, right? And then what I consider to be a nice compromise are piecewise Lipschitz graphons and graphon signals, right? Because at least you still have exchangeability or permutation equivariance with respect to these pieces. And there you get this rate that will depend both on, will be proportional to the number of pieces and inversely proportional to square root of n. Okay, but the core result is obviously, all these papers are slightly different, but if you could plug in any of these here, okay? Okay, so this is a note on the rates. But what is more interesting here is that the dependence on the Lipschitzness of the filter is very apparent, right? So we see that the transferability error, or the bound on the transferability error, is proportional to the Lipschitz constant, right? So the more your filter varies, the higher this bound. And it's also proportional to these terms that depend on the quantity c, which are essentially telling me, the smaller c is, the smaller the region where my filter has to be almost constant, right? So the smaller c is, the more discriminative my filter is. But then the larger nc is, so the more discriminative your filter is, right, through LH and through C, the larger this upper bound. So in other words, what this transferability upper bound is telling us is that there exists a trade-off between convergence and discriminability, or transferability and discriminability, right? Larger LH and smaller C, or more discriminative convolutions, lead to a higher error bound and vice versa. And this is just again, an illustration of this fact, right? So if I have a filter like this that is allowed to vary freely near zero, if I make a small error here in these eigenvalues and in the corresponding eigenvectors, that can be amplified very differently because the slope of my filter is not constrained in any way. But I have this later, I guess. Yeah, but if I make it less variable in this range, then I attenuate those errors coming from these spectral components. Okay. And then the second interesting part here is that in the finite sample regime, we always get this leftover, what I call non-transferable energy, which is not decreasing with n. And this is corresponding to those spectral components that are smaller than c in magnitude, which do not converge, right? So I wouldn't have this here if this function was constant in minus c and c, but because, okay, it has small Lipschitz constant, but there's still something there, right? So there's still some amplification of errors here. That's where that term comes from. So it vanishes asymptotically because I can make c vary with epsilon asymptotically, but not not in the finite sample regime. Okay, so all of this was for transferability of convolutions, and but very much like we were able to show GNN convergence from graph convolution convergence by just knowing that nonlinearities are normalized Lipschitz. The same thing holds here. We just have an additional dependence on the depth of the GNN, which I wrote L here, and on the width of the GNN, which I wrote D. But everything else in the bound is the same. So GNNs will inherit this transferability property from graph convolutions. Same discussion on rates and everything. But as much as this seems to imply that the conclusions that we make are the same, right? That we still have like this possibly bad discriminability transferability trade-off. Nonlinearities actually help in the spectral domain, and here, it's not theory; it's more like hand-wavy, but it has basis on like a strong intuition that comes from Fourier analysis, or in my case, from signal processing. So a typical type of nonlinearity that you have in signal processing, or that you use in signal processing, is, for instance, for converting AC signals into DC signals. Usually, the first step that you take when you have like a sinusoid like this is you kind of like I don't even remember what this is called, but you pass it through a rectifier and you get something like this, right? And then they do some like smoothing of the signal, but this, you can already see how this kind of like essentially creates a DC component, a non-zero DC component here, where there wasn't one here, right? And what happens in the spectral domain is that where before you just had this spectrum here of like a cosine, like the Fourier transform of a cosine, now the effect of this rectifier in the spectral domain is to take the energy that was all in these two components here and spread it throughout the spectrum, and particularly spread it to the high frequencies, because now you have these discontinuities here, right? So these discontinuities are modeled by high frequencies. So what we hypothesize is happening in GNNs is something similar. Once we pass the output of a linear graph convolution through a nonlinear function, that's going to have the effect of scattering the energy in some of these high frequency spectral components to the low frequency spectral components, where my filter is not restricted, right? So like imagine that I have a filter that is like flatter here, but here it isn't. And so in these regions, these components can be discriminated, right? Because I have enough kind of slope here, enough variability. And so this hypothesis could help us understand why in practice GNNs are more transferable than convolutions and vice versa, which it is indeed something that we observe. So for instance, in that movie recommendation example that I gave earlier, if you train just like a linear graph convolution, which I call graph filter here, and if you train a GNN for increasing graph size, you see that with all parameters staying the same, right? Same number of weights, same depth, same width, everything. The GNN is always more transferable than the graph convolution, right? So for the same graph size, training graph size, I make a smaller error. And you see this across applications in general. Here I have another example where GNNs are being used for decentralized robot control. So your inputs are like the nodes or the agent states, position and velocity, and you want to output the acceleration. And here again, we see that the GNN is more transferable than the graph filter. I don't have the actual performance here, but the GNN also does better than the graph convolution. So it performs better and it's more transferable. Let me see if I missed anything here. Yeah, I mean, another thing that I wanted to mention here is this Lipschitz GNN is just a GNN that we trained by penalizing the Lipschitz constant, which is essentially just penalizing the weights, right, like high weights. And so you also see that that is more transferable, which kind of agrees with the theory as well, right? Like the lower the Lipschitz constant, the more transferable. And what else? The other thing here that is interesting is that transferability is very useful because it allows you to train on much smaller graphs, right? And allows you to save computations by training on these smaller graphs and get similar performance than you would by training on the full graph. Here, the full graph is a 4,000 node graph, but we're not growing further than 2,000. Okay. Any questions? Okay. I think I have another 25 minutes. So yes?
I'm curious about the robustness of a graphon as we may have some perturbation or the noise that will be introduced to the graph model. Then what will happen to, it will lead to very different graphon, or it may be also correlate with the inherent stochastic with the graphon itself, so it may be ignored.
Yeah, that's a great question. So, like, essentially what you're asking is stability of GNNs to graphon perturbations, right?
Yeah.
Yeah. So you could, that's a great question that, I guess there has been some exploration, but not as much. But you would essentially use similar techniques, right? So you could essentially look at what the perturbation, what this graphon perturbation induces as perturbations of spectra, right? And use essentially the same techniques to see how stable your GNN is to those perturbations.
So we may trace the trajectory about the graphon itself and have to measure maybe by t-test, then we get some right robustness.
Right. That's a great point. So that's sort of right. Well, two things. So first of all, the graph that is defined by the communication graph that is defined by these agents is not a dense graph, so it doesn't come from a graphon. But I mean, this example I usually use to show people that, even though you have graphs that are not dense, you still see transferability in them, which is really nice. And second of all, if these GNNs weren't stable, you wouldn't be able to train these GNNs offline and then execute them while online, right? For new unseen trajectories. So this is hinting at the fact that yes, these GNNs are stable, and there are stability results for when you consider graph perturbations, but I don't think so much considering graphon perturbations. But they shouldn't be too different in flavor, I think.
Because graphon is more focused on the macro pattern of the whole graph,
so right.
This perturbation may be sacrificed. Okay.
Yeah.
Okay.
Thank you. Yeah.
Comment a bit more on the result of the learning by transference?
Yes, I'm going to talk about that now. Yeah. Okay. So, what else can we do besides transferability? So now what I'm going to talk about is extensions from these transferability results still in the realm of graphons, and some other uses of, more recent uses of graphons. The first extension closely related to transferability is the idea of learning by transference. So the idea for this comes from, the fact that your transferability error bound might still be too large for certain applications, such as multi-agent systems that usually have very strict safety requirements. So the question is, can you do better than transferability? And one way you could do better than transferability is you could actually leverage that convergence of graph sequences in the training of the GNN itself. So now instead of training on a fixed small graph and transferring to a large graph, we're going to train on a sequence of graphs, right, on the sequence of convergent graphs. And if you do that, you see that both empirically but also theoretically, you can show that as long as at each iterate, the error that you make in your graph gradient is at most norm of that gradient away from the true graphon gradient, then in a finite number of training steps, this algorithm will converge to an epsilon ball of the solution of the graphon ERM, right? Because ideally, you would want to solve the empirical risk minimization problem on the graphon directly. You can't do that. So you solve it on the sequence of graphs. And so as long as at each iterate you satisfy this condition, which is essentially saying your gradient estimation error can't be greater than the norm of the gradient itself, then you get convergence. Is that Does that answer the question? So here, the key thing is using transferability to prove convergence of gradients, and convergence of gradients then allows you to show that the solution of this graph sequence ERM problem is the converges to an epsilon ball of the solution of the graphon ERM problem. And here's an example of how this has been used in practice. So again, we have that multi-agent system example. And on this center plot here, what I'm showing is the control cost, which we want to be small, corresponding to a GNN trained on the full 100-agent graph, here for 9 epochs, here for 30 epochs. And on these curved curves, the control cost per epoch that we get by training using this learning by transference algorithm, where here we're increasing the number of nodes by 2 per epoch, or 5 per epoch, or 10 per epoch, depending on the curve. And so what we see here is that with less epochs and smaller graphs, we're able to match these performances here, which is very helpful because we know that the time per epoch grows with the graph size, right? So we save more computations and we get good performance and get nice performance guarantees. Okay. Another thing that we can do with transferability and with graphons is we can extend the idea of spectral sampling. So there's a large body of work in first mathematics and then in signal processing looking at essentially extending sampling theory, like Nyquist-Shannon sampling theory, to graphs and graph signals. And the problem of these algorithms for large graphs is that they require computing eigendecompositions, which are costly. And so what we wanted to do with Thien and with Stephanie was to essentially use this idea of convergence of graph sequences to prove convergence of sampling sets. Because if you have convergence of sampling sets to a limit object on the graphon, then you can, for instance, obtain those sampling sets on the graphon directly, sample from them to get sampling sets, unique sampling sets on your large graph or a small graph. And the reason why you might want to do that is because that, for instance, can improve the term depending on the signal error in your transferability bound. And it will allow also for a smaller training graph size n, depending on the shape of the uniqueness set, right? So typically, for instance, for 1D signals, if you know that your signal has frequency f, like the Nyquist rate is like 2f, right? So you know that you can get samples of at least that frequency, and here the idea is similar. You essentially get a lower bound on the number of samples that you can get. So this is just a continuation of this previous slide, right? Like here we're defining this notion of sampling sets for graphons. Now you can think of them as these intervals or disjoint unions of intervals from the unit interval where the signal, where if you know the signal, it essentially defines the signal over the entire node sample space. And what we proved in this paper was that if you have a sequence of convergent graphs converging to a graphon, there exists a large number of nodes such that a uniqueness set for this graph Gn is also a uniqueness set for any other larger graph in that sequence. And to prove this result, what we used was we used this nice relationship between graphons and kernelized mixture models, and result on the consistency of spectral clustering for these mixture models to show essentially consistency of Gaussian elimination, which is what you use to obtain these sampling sets. Now, another thing that you can do in that, yes? Yeah.
Nice set of samples.
More or less, you have to fix the labeling, right? So you would essentially, so if you have your large graph, you look at the induced graphon, right? And that would give you like what parts of that induced graphon are your uniqueness sets, and then you would have to sample from them.
I see. But once I work up with the induced graphon, this give rise to an explicit procedure, which.
Yes, if you continue like sampling or discretizing in the same way from the unit interval, yes.
Okay.
Yeah.
Thank you.
You're welcome. Okay, so here's another use of graphons. So here, Ron, I don't remember his name, and Gita have used graphons also to show, to derive results on the generalization of message passing neural networks. So essentially what they showed is that if you are training a GNN for graph level tasks, then the generalization gap of that GNN is upper bounded by a term that decreases both with the number of training samples, but also with the graph size, right? So the larger your graph, the lower the generalization gap. So that, so essentially, like what they show is that they significantly shrink the generalization error, right, beyond just the number of training samples, even when models are complex, where the complexity of the model is encoded by this constant C. And finally, another application very related and kind of like derived from transferability is essentially trying to show convergence and transferability of the graph neurotangent kernel. So I think most of you have heard about the neurotangent kernel, or NTK. It's defined as this outer product of gradients of your neural network with respect to the learnable weights. And what Jaco and others have shown is that in the infinite width limit, this kernel becomes constant regardless of the iterate. And this has two implications. One, that the learning dynamics of the neural network are deterministic. And two, that learning it via gradient descent is equivalent to kernel ridge regression. This is also true for CNNs and GNNs. I think Belking and others have shown this extension of the results. And what we did here was we tried to analyze convergence of the GNTK to a limit object, the graphon NTK, because then that can, the idea here was that, okay, we can use the graphon NTK or the NTK on a small graph sample to say something about learning dynamics on our large graphs, right? And so what you can prove is that for sequences of graphs converging to a graphon, the GNTK does indeed converge. What is more interesting is that its spectrum also converges, and the spectrum of the NTK is associated with the directions of fastest learning of the GNN. And so, and this is what you can see here, where we did these experiments on citation networks. Like you can see that the eigenvalues of the NTK are converging as we increase the graph size. And so the idea here, like a possible use case, is to estimate the speed of convergence of a large graph GNN from the eigenvalues of a small graph GNTK. Yeah.
Do you observe something like some frequency bias? That the smaller eigenvalues converge faster in a sense?
That is a great question. I have not looked at convergence of individual eigenvalues. I would imagine that they do, just because I was thinking of Davis Kahan.
They are simpler.
Yes. But yeah, that's a great question. I think that, I mean, typically what we observe is that if you have these like graph machine learning tests that depend on low frequency information, meaning like community detection, right? Just like the top eigenvectors. You see the GNNs do very well at that. So I would expect that there's, and they transfer very well, right, in those tasks. So I would expect that there is something like that. But I'm not aware of like any rates depending on magnitude. Thank you. Okay, so the final thing I'm going to talk about is something that is both old or traditional and new, which is using graphons for graph generation. So more recently, graphons have also been used in the context of graph generative models, where the goal is to learn the graphon from samples and then use it as a generative model, right, as a generator. But the reason why this is not a new problem is because the core problem here is the graphon estimation, which is the kind of canonical problem, right, like for graphons. Like the first few papers on graphons were on graphon estimation. And this is not an easy problem. Like there's some important challenges. The first one is that the graphon is non-identifiable up to measure preserving transformations. And the second problem is that you're trying to estimate a continuous model from discrete samples. As much as this problem is difficult, it has been extensively studied. I'm not going to cover the entire literature, but a few interesting approaches are, for instance, one of the first ones by Wolf and O'Hady that assumed Hölder continuity of the graphon and did maximum likelihood estimation by essentially averaging on groups, on k groups of a few nodes over a subset of permutations. Another approach tried to estimate an SBM from the graphs by making some piecewise Lipschitz assumptions on the graphon and measuring the similarity between graph slices. So they would essentially look at rows of the adjacency matrix for different graph samples and see if they match in some norm. And then if so, like that's an indication that those nodes should be in the same community. And then another one, which I find the simplest, is sort and smooth, which essentially is kind of making this underlying assumption that if you sort your nodes by degree, you should obtain like a continuous graphon. So they sort the nodes by degree and then they do L1 smoothing. So this is what they're doing here. Have observed graph, sort by degree, and then do smoothing to get the graphon. And then more recently, people have been doing this graphon estimation for generation via, for instance, implicit neural representations, right? So, for instance, Yuzu and others have this work that trains an INR, where the INR is now your graphon, right? Like the neural network is your graphon. That is such that what you give as an input to this INR is the coordinates. And what this model is expected to output is essentially the graph sampled from the graphon at those coordinates. And this is trained by optimizing the Gromov-Wasserstein 2 distance between what should be your real sample versus the predicted sample. And then more recently, people have extended this approach also using INRs, but now training them by calculating homomorphism densities for a few motifs and treating them as graphon moments to do moment matching. This is a very recent paper, but I thought it would be interesting to bring it here. Now, this is one of my final slides. So one thing that I would be remiss if I didn't talk about is that graphons have limitations. The obvious limitation is that even though they're good models for limits of dense graphs, they're not suitable for sparser graphs, which are most real-world graphs. So knowing this, people have carried out analysis for many other graph limits and random graph models. Similar flavor analysis with this idea of like looking at convergence of spectra, convergence of operators, have been done for other graph limits, some more general, allowing even for moderate sparsity, so with log n average degree. So for instance, there's this paper that I think first used the word transferability that looked at graph neural networks in general topological spaces. There's a paper by Kervin and others that looked at graph neural networks on GNP, where P can vary with log n over n, so these graphs can be moderately sparse. There's the work by Ji Young and myself, where we look at graphs sampled from or converging to manifolds, which also can be moderately sparse. And then some work that we did with Ruiz and Soleil, where we looked at something very similar to L2 graphons, so graphs that allow you to have a sparse periphery but still have a dense core, which allows you to say things about convergence of spectra. And this is the case, for instance, of degree-corrected SBM. For truly sparse graphs, which are graphs with bounded average degree, right? So where the degree is constant, the average degree is constant. The convergence is typically defined through distribution of rooted k-balls that are required to converge for every fixed k. So it's a much more local sense of convergence.
What are rooted k-balls?
So these are balls, like you sample a node and you say that's my root node, and then you start looking at the neighborhood of that node, right? And you look at the distribution of those neighborhoods. Papers or works using this idea are this one here that is more of a signal processing paper, but it does signal processing and graphings, which are limits of graphs with bounded degree, not bounded average degree, but bounded degree. The max degree is bounded. And a paper that Yagane is going to talk about tomorrow, which is GNN convergence under this Benjamin Ishram or local weak convergence paradigm, which applies to graphs with bounded average degree, but where you need your functions to be local functions. So they have to be local functions of these rooted k-balls. And then more recently, Thien and Stephanie introduced a unifying theoretical approach that uses graph operator limits. The interesting thing about this approach is that it can particularize to graph limits with varying levels of sparsity, from graphons to local limits. But it requires some additional assumptions on your graph operator, which doesn't have to be a linear operator. But if you have any questions, you can ask Thien about it. Yes?
So in these results, do we also get eigenvalues, so something of spectral?
No. So in these ones, yes. Like these ones that I mentioned in this slide use either operator or spectral convergence. That's kind of like the toolbox. These ones, they really use like convergence of measures and local functions defined on these rooted k-balls.
So there is no notion of spectrum in the limit even?
I am not aware. I know that there's things like spectral measures and things like that, but that's beyond my knowledge of this. But I think Thien might know.
For lots of sparse graph limits, the eigengap, for example, is not continuous. Hard to have a spectral graph convergence analysis similar to the graphon case.
Okay, and then as a final thing, I just wanted to say we're co-organizing this workshop at NeurIPS this year on graph machine learning, and I think it would be the submission deadline is the September 2nd, so in I guess a couple of weeks, and it would be great to get submissions from people here so we could continue this very nice workshop perhaps at NeurIPS in December. Thank you very much.
Now we have a coffee break for half an hour. Thanks a lot.